right, so the first section of tonight's homework is just a matching section, which is something that's pretty common on an AP test. You're given an equation and then you have to pick the correct multiple choice graph to go along with it. So if we just get started going through these, I'm noticing that number 9 is the only linear function and there's only one graph that's linear. So number 9 has to be f. It's got a negative slope, so that checks out. Number 10 is a quadratic, opens up. The only other quadratic I see is 11, which opens down. So 10 is a quadratic that opens up. That's got to be H. I'm sorry. Oh yeah, wrote that in the wrong spot. So 10 is H. 11 is a quadratic that opens down, so that's got to be C. 12 is cubic. I see one other cubic choice. So 12, I'm not worried about limit notation when I'm just picking graphs. It's rising on the right and falling to the left because of its positive coefficient, and it's makes it rise on the right, and its odd exponent makes it do the opposite on the left. So number 12 is A. Now I see that B has the same end behavior, but remember in our notes we talked about if it's degree 3, you can only have at most 2 relative extrema, so 1, 2, whereas this has 1, 2, 3, 4, so that's got to be a higher degree, that's got to be degree 5. So 12 is A, and where'd my other cubic go? 14, I'm skipping a little bit. 14 is the cubic that is going down on the right and has to go up on the left. That's got to be D. Now back to 13. That's degree 4. It's got to be opening down. So it might be a W shape or something with some fluctuation like these, opening down. And again, we have 1, 2, 3 relative extrema, relative max and mins, which corresponds to a degree 4 polynomial. So 13 has to be E. We did 14 already. 15 has to be opening up. Now this one, it's hard to tell if there are more relative extrema in here. Remember, the rule is at most 3 relative extrema for a degree 4. It could have less than that. So 15 is G. Really, I'm using end behavior to base most of these off of. And that leaves us with 16, which is B. End behavior matches up on the right, down on the left, 4 relative extrema variations. Okay, so once we do 9 through 16, the next on our list is 19 and 20. So 19 says we have g of x, which is negative x to the third plus 4. Sketch the graph, describe the transformation. Okay, so I'm going to describe the transformation first. So this graph has been reflected across the x-axis because the negative is out in front. And I've seen some of our AP questions that give you the order in which the transformations are happening. So this graph has been reflected first, and then it has a vertical shift up 4. And so then to sketch that, remember our cubic graph has a handful of nice points. The center of the graph is 0, 0, but now this is going to move up to 0, 4. Something like that. Normally we have the point 1, 1. So shift that up 4 units, you're going to be at 1, 5. And at negative 1, you're going to be at 3. Now, normally we're at 2, 8, so we're going to be like way up at 2, 12. I'll just plot that up there, pretend that's up there. And at negative 2, instead of at negative 2, 8, if you go up 4, you'll be at negative 2, negative 4. So it says to sketch the graph. I still like to put in some tick marks. I might not have this 12 high enough, but that's good enough. Okay, and then our next one is 21. So this says g of x equals x minus 2 cubed minus 3. So again, I'm going to describe the transformations first. These could be happening in either order, it doesn't matter. We're shifted to the right 2 units and down 3 units. So same points for my parent function. Oops, I just realized for number 19, I never reflected it. Sorry, goodness. Okay, I've already shifted up 4. So if I'm going to reflect at this point, I'm no longer reflecting across the x-axis. I'm reflecting across where that line of symmetry would be. So this really should have been like this. I guess this is why part of why I had someone at a conference say they liked to do their real-time homework videos, because then, like, common mistakes, hopefully common mistakes, that students tend to make, you can show yourself making, and there's things to look out for. So the green graph is correct. When I post these notes, I will probably, I guess I'll just get rid of my red graph. Normally I say do the reflection first and then shift, because it would be wrong to have shifted to go up 4 and then shift across the axis and have my graph be way down here. Okay, anyway, with that in mind, this graph has not been reflected. So instead of the first point being at 0, 0, it's going to be right 2, down 3, right here. And then I usually just build off of that center point. I have it memorized from the parent function that the next point from the center there is right 1, up 1, left 1, down 1. So I'm at 3, negative 2, and 1, negative 4. And then again, I do 1, right 2, up 8. So I go up 1, 2, 3, and then 1, 2, 3, 4, 5. So at 1, 2, 3, so you should have a point at 4, 5. And then 1, 2, so on the y-axis here, 1, 2, 3, 4. So we need to go down 8. 1, 2, 3, 4, 5, 6, 7, 8. So that should be at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which makes sense since we shifted down 3. Okay, so here's my final graph for 21. The next problem that we're doing is number 30. So number 30 gives us this function, h of x equals 1 minus x to the 6th. And then the directions here say, just pull this up here. Describe the left hand and right hand behavior. Use a graphing utility to verify. So I'm not going to verify on my graphing calculator. You're welcome to. I actually don't have a working one on my computer at the moment, so that's unfortunate. But the left and the right hand behavior, let's use our limit notation. It doesn't specify that in this book, but let's get used to doing that. So you don't have to mark which is right and which is left. I just want to make sure that you know which is which. So I always start off with the right hand. The limit as x approaches infinity, this describes the right side of the graph approaching infinity, of h of x. You've always got to have something here, either h of x or right 1 minus x to the 6th. So what should this graph be doing? You can kind of sketch it off to the side. This is the leading coefficient. We should be going down on the right and doing the same thing on the left. So that means that the graph is approaching negative infinity. And the left-hand behavior is the same thing, but you write it as the limit as x approaches negative infinity, because that just means as your x values fall, as you trace them to the left, your graph is going to be falling down. So the limit of h of x is also equal to negative infinity. Informally, we would say that we're falling on both sides. Okay, we're also going to do 34. 34, I just wanted to make sure that you knew how to simplify something like this. So this says 3x to the 7th minus 2x to the 5th plus 5x to the third plus 6x squared. It's all over 4. So not that, I guess this isn't as exciting as it could have been, but the fact that all of this is divided by 4, remember that does mean that if you needed to for some reason, that's the same as dividing every single term by 4. So some of these terms would reduce, but some would not. Sometimes I get students that want to, back when it was all divided by 4, go back to the original here. Sometimes I get students that want to say like, oh, I can reduce this, just those two, but that's not true. That's just on that term. So just be careful with that. Okay, anyway, our leading coefficient is right here. Technically, there's a 3/4 in front of it. That doesn't change anything. It's really just about the fact that it's positive or negative. So our right-hand end behavior, because this is an odd exponent and positive, the right side rises up. The odd exponent forces the left side to do the opposite. So the right-sided first is the limit as x approaches infinity of f of x. I would definitely write that instead of the entire equation. We're headed toward infinity for the graph. And the limit as x approaches negative infinity of f of x, because the graph, the y values are falling down, negative infinity. Okay, we're also doing 36. F of x is equal to negative 5/6. Excuse me, it's f of s. F of s is equal to negative 5/6 s to the third plus 7s squared minus 8s plus 1. You have to think of this as if you were to distribute this through, but again, the only thing that matters is the leading coefficient. So I'm looking at a negative 5/6 s to the third minus some other stuff. So s to the third on the right side will fall down because this is negative, and the left side will do the opposite. So our right-handed end behavior is the limit as x approaches infinity of f of s. Oh, and this shouldn't be x. Again, all these little details kind of matter. This should be s. We're talking about the inputs, and the inputs for this function are s. The limit as s approaches infinity of f of s is equal to negative infinity. On the left side, the limit as s approaches negative infinity of f of s is equal to positive infinity. All right, our next problem is 51. No, 56. 56. So we have f of x equals x to the fourth minus x to the third minus 20x squared. The directions for 56, let's just look at these. Say, where'd it go? Find all the real zeros, determine the multiplicity. We're not going to do the last part. If you want practice doing it though, use a graphing utility to verify your results. So if we want to find zeros, we need to show that we're setting the function equal to 0. Don't just start factoring and solving without an equation. So first we can factor out an x squared. That's the GCF. That makes this trinomial much easier to factor. And we set each factor equal to 0. So from the x squared, x equals 0. If x minus 5 equals 0, x equals 5. If x plus 4 equals 0, x equals negative 4. Excuse me. Describe the multiplicity at each one. So I'm just going to abbreviate here for my homework. Multiplicity is 2 for 0, and it's 1 for x equals 5, and it's 1 for x equals negative 4. And let's see, did we need to? No, we didn't have to describe. But if we did, informally, bounce, cross, cross. More formally, function does not change signs. Or I saw another explanation, the function is tangent to the x-axis. I like that, at 0. And then the function does change signs on either side of 5 and -4. All right, next one is 57. So 57 is f of x equals 1/2 x squared plus 5/2 x minus 3/2. Same directions as before, so set this equal to 0. You have two ways of thinking of this. You can say I'm going to factor out a 1/2. When you factor a 1/2 out of everything, it's the same as saying I'm going to multiply each term by 2. So like if I factor the 1/2 out of x out of the 1/2 x squared, that's x squared. If I factor 1/2 out of 5/2, I get plus 5x minus 3. Because it's an equation that we're setting equal to 0, you could have also just said if this equation equals 0, I'm just going to multiply both sides of the equation by 2, and you can get rid of this 1/2 altogether. The 1/2 doesn't really matter as far as finding zeros, so I'm just going to be looking at this. Now, this doesn't factor, so remember, back in our quadratic unit, if something doesn't factor, it doesn't mean that we can't solve it. We use our quadratic formula, so -5 plus or minus square root of 25 minus 4 times 1 times -3 all over 2. Underneath the square root, this becomes, I always just do this off to the side to save some writing. This becomes 25 plus 12, so that's 37. So -5 plus or minus radical 37 all over 2. Now, what's the multiplicity on that? If we were to like show this factored out now, here's how it factors. We don't normally do this, but it's like normally if 5 is a 0, you got x minus 5. If -4 was a 0, x minus -4. So I'm going to write it like this. X minus 5 plus radical 37 over 2. X minus -5. Oh, sorry, this is -2. -5 plus radical 37 over 2. X minus -5 minus radical 37 over 2. Did you have to write this out for this problem? No, but remember, you're supposed to not only identify the zeros, which we did, you're supposed to identify their multiplicity. So I'm just showing you that even if something doesn't obviously factor, you can, once you find the zeros, you can go back and write what the factors would be. It's just x minus the 0, even though it's kind of ugly looking. And the reason I'm doing that is just to show that the multiplicity on each of those factors is 1. For both of those. So this graph is a quadratic. It would cross through the x-axis and change signs at both of those values. Okay, 58 is our last one in this section. F of x equals 5/3 x squared plus 8/3 x minus 4/3. So kind of the same idea as before. Set this equal to 0. And then let's just say, instead of factoring out a 1/3, let's just say we're going to multiply both sides of the equation by 3 to clear out the fractions. You're doing the same math, you're just showing that step, that taking out of the fraction, you're just showing that step differently, whether you're factoring it out or multiplying both sides of an equation. So it would still be 0 on the left side, and that would give us 5x squared plus 8x minus 4. Now we've got to think if this thing factors at all, so let's see. Now we could just jump right to quadratic formula, but the numbers are going to be kind of big, so if I can avoid quadratic formula, I would like to. 4 can be split into 2 and 2. 10x, 2x, I want to get plus 8x, so yeah, so if I make this plus 2 to get plus 10x, and I make this minus 2 to get minus 2x, that will give me the 8x that I need. Okay, so this does factor, that's great. So the zeros are 2/5 and -2. If 5x minus 2 equals 0, you would add 2, divide by 5 to solve for x. Each of those have a multiplicity of 1. So that finishes that section. Our next problem is number 60. So 60 says, use a graphing utility to graph and approximate the functions. I can't do this at this time with my graphing calculator on my screen, but I will put this into Desmos and show. Again, my graphing calculator, it's summertime and it's not working. So anyway, so I can put this into Desmos. Let's see. And this is what you can do if you left your graphing calculator at home. It does not mean you can't do your homework. F of x equals, we're doing 60, so negative 3/8 x. Where did you go? Negative 3/8 x to the 4th minus x to the 3rd plus 2x squared plus 5. If I were putting this in my graphing calculator, I would just zoom 6, which is the standard. That is getting it into a 10 by 10 window. And I can see an approximate answer of negative 4.142. I'll write that down. Let's see, what did I say? Negative 4.142, and the other one, 1.934. I use this little wavy equal sign as an approximation, so that's what I got for 60. I really just assigned this one to make sure that you knew how to switch your window around, practice finding zeros, that stuff you need to do for our AP test, along with next year's AP test for calculus. All right, next we're moving on to 68. 68, we didn't do this in the notes, but we're kind of thinking backwards here. I actually did it in a more complicated way for number 57. For 68, they give us 3 zeros of the function. It says find a polynomial function that has the indicated zeros. There are many correct answers, so we'll talk about why that is in a second. But if I'm given the zeros, remember this is saying like x equals 0, 1, and 8. And if those are the zeros, then I'm going to call my function f of x. It means that the factors must have been an x that got factored out, an x minus 1, and an x minus 8 to produce, when you set this equal to 0, to produce those zeros. So this is one possible answer. The reason there are many answers is because it doesn't tell us a certain degree that the polynomial has to be. So I could put any exponents I want on this. I could make it crazy as long as they're positive, integer or positive whole number exponents. I could also put like a coefficient out in front if I want to. So it really does not matter what you choose. You can just go with the basic version without all the extra stuff in it too. I'll probably have that for my final answer on the key that I post, but that's why there are many answers. Okay, what about something like 72 though? 72 is more complicated because the zeros are more complicated. So it says the zeros are 4 plus radical 3 and 4 minus radical 3. And so I'm going to go back and look at 57 like I did before. When we had this really ugly set of zeros, remember we could just write the zeros as x minus each of those. So I want to start there. Let's call this one h of x. So in its factored form, I could say x minus, and then I've got, this is not a fraction, so before, when I had a fraction, I just put the minus sort of out in front of the fraction. Here I need parentheses around the quantity. We're subtracting all of that, 4 plus radical 3. And the other factor would be x minus the quantity 4 minus radical 3. All right, and then I don't like having negatives in parentheses, so let's clean that up a bit. X minus 4 minus radical 3, x minus 4 plus radical 3. which is kind of like, isn't that what I would have just had if I didn't use parentheses? And yes, that's true, but we're just kind of being careful and technical about things. Now, it doesn't say to write this in polynomial form, but I just want to show you a quick trick. So this is correct. But what if I'm on a multiple choice problem and I'm supposed to find the answer, but all of the answers are the FOILed together, the multiplied, the general form version of this answer? The long way would be distribute this x all the way through, distribute the 4 all the way through, and the radical 3, and combine like terms. Hope that you did it correctly. The shortcut, though, is to say, what if we look at this a little bit differently? What if we look at this as x minus 4 minus radical 3, x minus 4 plus radical 3. So like think of the x minus 4 as a whole thing. If I told you to multiply this together, a minus radical 3, a plus radical 3, those are conjugates. Remember? Well, I don't know if how much we've used this. We're going to use the term conjugates a lot this year because conjugates multiply together really nicely. A times a would be a squared. You'd get a plus radical 3a, a minus radical 3a, so those cancel, and then you'd get minus radical 3 squared, or minus 3. Well, the same thing is happening here. I've got, instead of a, I've got x minus 4. So it's going to become x minus 4 times x minus 4, x minus 4 squared. You're going to get a plus radical 3 times x minus 4 and a minus, so that's gone. And you're going to get a minus radical 3 squared. And then this is a lot simpler to FOIL out, distribute out, if I'm looking for the correct answer in a multiple choice selection. So, what about for our quizzes and tests? If it's a problem you're filling in, writing in the answer, if I don't specify, you can leave it back here in its factored form. If I do say write the general form polynomial equation that has these zeros, then I want this form. Or maybe I'll have a multiple choice question and that will force you into one form or the other. So just be looking for those. Okay, our next set of problems, that was 72. 75 and 77. So let's take a look at 75. We're given a list of information. We have a 0 of negative 4, multiplicity of 2. We have another 0 of 3, multiplicity of 2. And we have to make it degree 4. The directions say find a polynomial function with the indicated characteristics. Again, for the same reasons, there could be many answers. You could put any sort of coefficient out in front, and you would create a slightly different answer than what I have. So let's start with the zeros. Well, first of all, let's make it a function. Let's make it, I'm going to call this one c of x, whatever. C of x equals, one of the zeros is negative 4, so x plus 4. Multiplicity of 2 tells you what exponent has to be on it. The other 0 is positive 3, so x minus 3 is the factor. Put an exponent of 2 on there. Now this is already degree 4 because if we were to FOIL this together, we'd have an x squared times an x squared. And so I'm going to leave my answer like that. I can't introduce any extra x's because that would make it degree 5 or higher. I could put any sort of coefficient I want in front of this, like a 3 or a 1/3 or a negative 2, whatever. Or I could just leave it like this. Okay, we're also doing 77. 77, we've got, I'm going to put z for zeros. 0 of negative 1, m is multiplicity, multiplicity of 2. 0 of negative 2, multiplicity of 1. Degree 3. Extra stipulation, it's got to rise to the left. That means on the left it's got to be going up. It's degree 3, so I'm going to give myself some more information. If it has to rise on the left, it has to go down on the right. in order for it to go down on the right, I have to make sure I put a negative coefficient in front of that leading term. Okay, so f of x. I'm still going to start with the zeros. So I've got x plus 1 as a factor. It's got to be raised to the second power. And x plus 2 as a factor to the first power. So it's already degree 3. These add up to 3 for the exponents. And then again, I have to have some sort of negative number out here. So I'm going to make it negative 1/2. You can make it just a negative 1 or any negative number that you want. All right, next we're moving on to 84. 84 says g of x equals x to the 4th minus 4x squared. Part A says apply the leading coefficient test. B says find the real zeros of the polynomial. C is plot sufficient points. Draw the continuous curve. So basically graph this thing. Okay, so I'm just graphing. So I'm going to informally do my end behavior. Should be rising on the right and the left because of the positive x to the 4th. I'm going to figure out my zeros by setting this equal to 0. Factor out an x squared. We have a 0 of 0 and plus or minus 2. At plus or minus 2, the graph is going to cross. At 0, it's going to touch and turn or bounce, meaning it should not change signs at 0. It should change signs at both plus and minus 2. Whoops. And then for my sketch of my graph here, so I've got my point at 0. I've got my 0 at 2, and negative 2. The zeros that are the farthest to the left and the right have to be where your end behavior is drawn from, because there can't be another 0. That would mean that we'd have something else that we can factor out. So I know that I can do my end behavior from there if you want to. And then I just need to evaluate what is g of 1 and negative 1. Let's start with negative 1. Now this is an even function. So I'm going to get the same answer whether I plug in 1 or negative 1. I'm going to get 1 minus 4 times 1 in both cases, actually, right? So 1 minus 4 is negative 3. So that's pretty easy. I can plot those. Now just connecting the points, you sort of get what should be happening at each 0. So you should have like a W-shaped graph. It should be smooth. Make sure you're not making it like a true like linear W. And that's it for 84. Next one we want to graph is 89. 89 says f of x equals x to the 3rd plus 3x squared minus 9x minus 27. Again, we're just supposed to graph, so I'm going to informally do the end behavior. Because this is positive x to the 3rd, the graph rises on the right, falls on the left. To get the zeros, I need to factor by grouping. You can take x squared out of the first two terms. You can take a minus 9 out of the next two terms. And then this factor by grouping allows us to factor a GCF out. Now we can factor out the GCF of x plus 3. And we'll be left with x squared minus 9. That factors further. Because this is x plus 3, x minus 3, and I need to consolidate like factors, I'm really going to have x plus 3 squared times the x minus 3. Because I already had an x plus 3 here. There's another one in this factor difference of squares. And so that means at negative 3, the graph is going to bounce, be tangent to the x-axis, whatever. And at 3, it's going to cross. Okay, so 1, 2, 3, 1, 2, 3. Plot my zeros. Short little end behavior sketch. We need all these points in between, so f of negative 2. Now, when you're plugging in f of negative 2, you could go back to the original, Or I kind of like to do into the factored version. The math is usually easier. Negative 2 plus 3 is 1 squared. Negative 2 minus 3 is negative 5. So I've got the point negative 2, 1, 2, 3, 4, negative 5. I'm going to do the same thing here. Plug in negative 1, I get 2 squared times negative 4. 4 times negative 4 is negative 16. So, okay, my tick marks are going to be kind of annoying now, so I have to go down, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It might be a good idea if you're sketching the graph. Don't want it to take forever with all of your tick marks. Actually, I'm going to go back and do this because I see the next one coming. Find all of your points first, and then you can decide how extreme you want to make your axis. We are just sketching, right? Why did I say that? Because f of 0, if you plug in 0, I would go back into the original because 0, 0, 0. That's negative 27. I don't want to make 27 tick marks, so we'll deal with that later. Plug in 1, you get 4 squared times negative 2. Don't want to make 32 tick marks. And finally, f of 2. 5 squared, 25, times negative 1. So I'm just sketching the graph. Here's how I would do it. I would say, okay, where's our lowest point? At 1, we're at negative 32. I'm calling this negative 32. Just label it like that. And then at 2, we're at negative 25. Okay. I'm just going to say that's like here-ish. At 0, we're at negative 27, so make that a little bit lower. At negative 1, we're at negative 16, so okay, maybe here. And then negative 2, negative 5. Again, these are sketches. Just the fact that I'm having you find all of these points is probably more than you would ever have to do on an AP test, but it's just good practice to be able to plug points in. Okay, let's see, 91. 91 is g of t equals negative 1/4 t to the 4th plus 2t squared minus 4. End behavior, down on both sides. Zeros, we can either factor out a negative 1/4, or we can say, when I set this equal to 0, I multiply both sides by negative 4, because I don't like a negative leading term. If I do that, this becomes t to the 4th minus 8t squared plus 16. This is a trinomial. T to the 4th gets split into t squared, 16 into minus 4, minus 4. Each of those are a difference of squares, and since there are 2 of them, we're going to have 2t plus 2's and t minus 2's. So the zeros are at plus or minus 2, and the graph is going to bounce or be tangent to the x-axis at both of those values. Now, when you're plotting the zeros, go ahead and make your tick marks, because the horizontal tick marks don't have to represent the same distance as the vertical ones. So those are the zeros. What about the points in between? Because so far I have this. So I'm going to take my advice from last time and figure out the values first before I plot them. If I plug in negative 1, I'm going into my factored form again because I like that. And I don't want to deal with the fraction to begin with. Oh, no, wait. Sorry. Scratch that. Okay, here's one stipulation. I did not divide away a number in the original graph to find the zeros, so I could plug into the factored form just fine. If I plug into this factored form, I'm missing the 1/4, the negative 1/4 that was originally there. So I do need to be careful. You can do that when you're solving for zeros, but you do need to go back and plug this in or show yourself that there's really a negative 1/4 out in front of this. To be safe, let's plug into the original. So we have -1/4 times 1 plus 2 times 1 minus 4. So because I'm graphing, I'm going to go with mixed numbers here. -1/4 plus 2 minus 4, or minus 2, is -2 1/4. That's easy. Excuse me. That's easy to think of if you're plotting. Just make sure it's between -2 and -3. If I plug in 0, that's easy. That's -4. And if I plug in 1, I get the same thing, right? I still get -1/4 times 1 plus 2 minus 4. So -2 1/4 is a little bit past -2. Oh, I didn't do 0. Oh, I did do 0. Gosh. 0 is at -4. I thought that looked a little strange. So something like this. All right, now we're on to the applications. Again, I don't have my graphing calculator, so you would be allowed to use a graphing calculator, I think, for these if they were on an AP test, so just kind of bear with me. 108. So this is a classic problem. We've got this open box made from a square piece of material, 24 inches on each side. You're cutting squares from the corners and folding along the dashed lines. This is slightly different than this one where you're cutting off the corners and just folding up. You can see the dimensions are like x here and then 2x over here. So write a function that represents the volume of the box. So that second x flap is being folded up and over. Okay, so when we're looking at our dimensions, we're still, hold on, let me draw this picture here. So when we're looking at our dimensions, let me have something to write on. This was 24. But then there's this sort of inner rectangle, and I am not really correctly drawing mine to scale, but okay. So from the 24 side, it shows you x and x like this. So this new dimension is going to be 24 minus 2x. On each side, sorry, so 24 minus 4x, because it's minus 2x on each side. And then this dimension, there's just an x that we're cutting out, but this was 24 as well. So this dimension is 24 minus 2x, right? So clean that up a bit. So when you do 24 minus 2x, you get minus 4x. And then when you do 24 minus x, that's 24 minus 2x. But then be careful here. The height of this box is not going to be 2x. When you fold it up, if you look at their picture, the height, because they're folding that extra x tab down, the height is still just x. So because volume is length times width times height, the volume, let's make it a function, v of x is going to be, I'm going to do the height first. X is the height. And then the dimensions of length and width really don't matter. I'm going to say 24 minus 4x and 24 minus 2x. There's no need to specify or to go through and like FOIL that together unless they tell you that specifically. That's part A. Part B says determine the domain of the function. So this application problem, x is not all real numbers. We know x can't be negative, right? Can't cut a negative space. That would be like what, taping on, I guess, adding on to the paper. So we know x has to stay above 0. And then what about for the function? You don't want a volume of 0. So if you take a look at these dimensions, so if x is 12, that makes this dimension 0. If x is 6, that makes this dimension 0. So we can't have any of the dimensions being 0. So even though this one can go all the way up to 12, this one's limited to 6. So we have to stay under 6. We can be like 5.9999, not until 6. Technically, we can be 5.9 repeating, but we can't actually hit 6. So that's our domain. And then part C says, sketch a graph of the function, estimate the maximum. I would do this on your calculator. I think we've sketched enough graphs here. I'm not too worried about that. But this would be, for our AP test, this would be a calculator and we would find a relative max or min. I will tell you, let's see, our textbook, I'm looking at the answer key here, says we should get about 2.54 for that maximum x value. That would be inches. Okay, and then 109. 109 is our total revenue. Let's see, let me write down this function. 1, 2, 3, 4. 1, 2, 3, 4. 4 zeros in front of that 1. Negative x cubed plus 600 x squared. They give us a domain. So if you're using your graphing calculator, I would type in this equation and set my x min to 0 and my x max to 400. All right, so this is the total revenue in millions of dollars for a company, and it's related to its advertising expenses by the function. X is the amount spent on advertising in tens of thousands. They give us a graph below. I should be looking at this here. Use the graph of the function shown in the figure to estimate the point on the graph at which the function is increasing most rapidly. That's a point of inflection where we're increasing most rapidly. Because look, this graph is concave up. The point at which it switches to concave down is when it would have the steepest positive slopes. So it's called the point of diminishing returns. We're just kind of estimating where we think that's happening. Let's see, do we really, I think it kind of looks like it's happening at 200. It's just an estimate, so I'm going to call it 200. X is measured in tens of thousands of dollars. So we're going to say the point of diminishing returns is about, let's see, do they want the points? They want the point. About 200, and I'm going to call that like 150. And so technically it's 200. The label would be like tens of thousands. So you could multiply 200 by 10,000 of dollars. Or if you're not sure, you just write 200 tens of thousands, but 200 times 10,000, so put 4 more zeros on that. $2 million is what we're looking at for their advertising expense for that point of diminishing returns. Okay, and then so we didn't really need the function because they gave us the graph there. 110, this says to sketch the graph, so I'm not going to write all of this, copy all of this down here, but it says the total revenue in millions of dollars for a company is related to its advertising expense. So here's the revenue function. Again, specified domain. X is the amount spent on advertising. Sketch the graph. Do that in your calculator. Practice fitting the window. So X min is 0, X max is 500, and then you choose zoom 0 for zoom fit, and it should show you a nice graph. Use that graph to estimate the point of diminishing returns. So again, where's your point of inflection on your graph? I don't have my graphing calculator right now to show you. Looking in the answer key for my book, it says it should be at about 250, 156.25. You would just use the trace feature on your graphing calculator to kind of find that. We don't have a specified function in that second trace menu to find like a point of inflection. Okay, our last section is true and false. So 113. It is possible for a 6th-degree polynomial to have only one real zero. I want to have these on my key, so let's see. Is it possible for a 6th-degree polynomial to only have one real zero? If you can think of an example, then that should work. X to the 6th, isn't that one real zero? 0 is to the 6th degree. So yeah, that's possible. It doesn't always have to be true, but it's possible. 114. Is it possible for a 5th degree polynomial to have no real zeros? If a function doesn't have real zeros, it needs to be able to be completely above the x-axis or completely below the x-axis. But remember, a 5th degree polynomial has to have either this end behavior or this end behavior. So at some point, it's going to have to cross back down through the axis. So that's false. Oh, oh, there we go. Okay, last two, true and false. It is possible for a polynomial with an even degree to have a range of all real numbers. This is kind of goes with 115. If it's next to the 6th, can the range, the y values, could those y values go to negative infinity? No. If it's something that is a W shape, whatever, yes, it can have some negatives, but it has a limit. Even degree means that you're not going to get the opposite end behavior that's going to cover all of your y values. So that's false. It's not possible. Last one. The graph of a function f of x touches but does not cross the x-axis. That's false. We cross at the odd multiplicities there and there. Okay, that's it for tonight's homework. We will go over anything you had questions on in class tomorrow.